So thanks for the invitation. I'm the technical manager from an HPC Center of Excellence within Euro HPC. And here to talk about EESSI. That the long form of that name is the European Environment for Scientific Software Installations. And part of the motivation for this was the changing landscape for scientific computing. So lots and lots of available software, particularly when it comes to things like reproducibility, which is being pushed continuously within the community. Reproducibility effectively means making your software available as well. So there's been an explosion in these kind of things, especially in domains like bioinformatics. But then also in like AI, we obviously seen a massive explosion in the usage and the impact of AI. And that brings with it like the entire software stack that comes with that community. There's also an increasing interest in the cloud for scientific computing, and that's because it's nice and flexible. So it's usually not necessarily cheaper. It depends on your usage, of course. But there's a lot of general interest because it is easy to use. In terms of microarchitectures, things are getting interesting again. So we're going beyond the traditional companies like Intel and AMD. We see a lot of ARM around, and you can no longer say it's coming; it's already here. So you've had that for a good few years in Fugaku, and you will see that this year in Jupyter. And RISC-V is on the way as well, so that's coming soon. And so we also have to look at that architecture as well. But the manpower that's available within HPC support teams, particularly when we think about like the large centers like Jülich Supercomputing Center, is always going to have substantial manpower and substantial projects connected to these new architectures. But smaller sites or locations, so like this is an example from the University of Ghent, which is like, say, a regional compute center in Belgium. They're getting about 400 requests for new software installations every year, which makes them really busy, right? Because the amount of people that they have working on the team hasn't really changed much over the years. So what should we do as a result? Well, we need to collaborate more, right? So a lot of people are doing very, very, very similar tasks in all these different sites. So we need to find a way to be able to collaborate together to solve these kinds of software stack-related problems. There's way too much software for a single support team to handle, but as a group, we can handle an awful lot more. And of course, there are different systems out there. We have these different CPUs that we've already mentioned. We also have different operating systems. We have different MPI layers because people have different hardware in terms of what they have in CPUs or in terms of what they have in the communication fabric. But then, of course, the same is true for accelerators as well. We have different generations. We have different providers for those accelerators as well. So there's lots and lots of different problems that result from the combination of all these different things. So I'm a maintainer of EasyBuild and have been for quite a long time now. And we kind of think that EasyBuild is not sufficient anymore. It was a good place for people to collaborate, but just that is not enough because there's still a lot of duplicate work that's taking place at HPC sites and then among scientists themselves as well. And the other thing is that there are really diverse software stacks across all these different platforms, right? So of course, we're talking about the HPC space where we have like central applications and people may build on top of that with their own tools, or they may completely move away from the central stack and use all their own stuff. So that might be the typical environment for that is a container, but then of course you can use other tools as well, which would give you the same end result. That's different to the environment where people develop code. So whether that's a desktop, a laptop, or where they also run these applications before they move to large systems. And then of course you have the cloud environments as well, where you're going to have the host operating system, but then typically you have a container on top of that. So that's another different environment where people are running applications. So then EESSI to the rescue. So what EESSI does is it gives us a compatibility layer on top of the operating system, and that's done for each family of CPUs. So right now we have actually 3 compatibility layers. So we have the x86-64 family, we have the ARM family AR64, and we also have RISC-V support now at this point. So we have a compatibility layer that means we get, regardless of the underlying operating system, we get our own operating system on top. And because we have that compatibility layer, then we can build a software layer that is independent of the operating system. And we can optimize that software layer, so the scientific software layer, for all of the different architectures that we support. So rather than just the family, we still support the family, but within that we support each individual CPU or instruction set really. So we've got Haswell and Skylake, we've got Zen 2, Zen 3, and we're working on Zen 4 now. In the ARM space, we've got generic, we've got Neoverse N1, Neoverse V1, and then we're about to start working Neoverse V2 as well. So we've got this, as a result then, we have a shared repository of optimized scientific software installations that are available across all these different systems. And the end user effectively, ideally, doesn't see these differences, right? Because they get the same software stack everywhere. So regardless of whatever CPU they end up landing on, they see the same software stack and they just use that. And that means, as a result, whether you're on an HPC system, if you have EESSI, you can use that environment. Or if you're in the cloud, you can still use the environment. It behaves in exactly the same way. Or if you're on your laptop or your desktop or in a virtual machine, you can get that same environment. So what are the ingredients that make this up? The first of those is the CVMFS, so CERN VM file system. That's basically a global distribution of our software installations. It's a read-only network file system. So that's the part that allows us to stream the scientific software. So basically that's a layer that allows us to get the software into the hands of the end users and dynamically update that software stack as well. How does it actually operate? So basically there's something called a Stratum 0. So there's a central server that has the main copy of the information, and then that copies it out to a set of servers that are what the end user actually talks to. So they are called Stratum 1 or mirrors. They're effectively mirror servers of the information that's in the main server. And then we have a sync server as well, so you can maintain your own mirror on your own site or within a particular cloud environment, or maybe in a region within a particular cloud environment as well. And then an end user, then whether they're on an HPC cluster or on their own machine or on the cloud, they will talk typically to a proxy server that will talk to our infrastructure. And if you're interested in learning a lot about HPC best practices when it comes to CERN VMFS, we have a tutorial on that, and the link is in the slides, and there's a YouTube video of a recording of that tutorial as well. The second ingredient then is the abstraction that we take away from the operating system. That's based on Gen 2 Linux, so Gen 2 prefix in particular. You can think of that in the same way that you think of a container image, but with the upside that you don't require a container runtime, and it doesn't abstract you away from the underlying operating system, right? So you can still see the file system, you can still see all the hardware on the host, and you can see all the drivers and everything as well. There are ways to get them through, but they're invisible to you, and without performing any tricks. The compatibility layer, so that's like containers without the containing. It's very small. It's just a minimal collection of tools and libraries. It does include glibc, so the only thing we really require from the host is the kernel. So it has Bash, it has Python inside. It's where we get our user interface as well. So we use LMOD, so we use the module environment as the end user interface. We have a compatibility layer for each of the families. So for the three I mentioned basically already. So we used to have Power as well, but we've dropped Power support because we seem to be using it. So we have x86-64, we have ARM, and then we now have RISC-V as well. The installations that we build in the software layer, we have sanity, or we have checks in place to ensure that the applications that we ship in that layer only ever link to things that are in the compat layer. That's what gives us the portability. That's done with our RPAT support. In terms of compatibility then, basically that allows us to have compatibility with any client system that's running Linux. And actually you can do that within WSL as well, so you can also run on Windows systems. And then the top layer then is our optimized software stack. We use EasyBuild to actually do the installations themselves. Our user interface is the module environment tool, so the specific implementation we use is LMOD. And then what we do at runtime is we figure out what architecture you're running on. So in the past we've used RISC-V to do that. We've actually developed our own little bash tool that basically does the same kind of work called ArcDetect. That's what we're using these days. So that'll automatically select the right software stack for the hardware that you're running on at any particular time. So what does the software layer look like? So this is all our scientific software. That's all the applications. They're optimized for the CPU targets where they're going to be run. They're running on any Linux layer because they only link to the compat layer. We use EasyBuild, we use LMOD, we use ArcDetect now, but you can still use ArcSpec if that's what you prefer. Basically, and as a result, then you're always going to get the best subset of software installations for the CPU where you're actually running. So what's new? So some of this you might have seen last year. I presented here last year as well. I gave a tutorial. I'm going to introduce some of the new things that we have this year. So one of the things that we have is a support portal. So you can actually ask for help when it comes to using the EC environment. You can report issues. You can request new software to be installed or made available. You could suggest additional features that we could implement. That's running under GitLab as opposed to, we typically do things under GitHub. But GitLab gives us additional capabilities, and particularly it allows us to have confidential tickets as well. So that's why we're using GitLab for our support infrastructure. And then in terms of the user experience of how to actually access and use the EC environment, you basically source you have to make it available somehow first, so you have to install CVMFS. But once you've done that, so if it's already available in the system where you're running, you need to source a particular location. So it's basically an initialization script that's currently only available for Bash. But that will then figure out what CPU you're on, and then allow you, and then expose all the modules for that CPU target, and then you'll be able to immediately start running things, right? So loading a particular module and start running your application. So in this case, it's TensorFlow. What actually happens in this case is that once you try and do that, to actually get the files that you need to run that application, immediately you're going to talk to what's called the local client cache, so to see if those files are available locally. And if that's the case, then you just start using it, you start running. If they're not available in the client cache, you start running. And then if they're not available in the client cache, that CVMFS will then talk to the mirror server to bring those files in locally. That assumes then of course, that the mirror server have them. That's automatically updated by the central server. So it periodically talks to the central server to see if there are any new updates and pull in those updates as well. And the end result is that EC is effectively providing on-demand streaming of the software that you have. So even though the files might appear that they're available, they're not really available until you try to access them. This had the added advantage, say, over containers, in that you only pull in the files that you actually use, right? So even though everything may appear to be there, you only pull in files that you actually use, which means that your runtime is typically quite small. So for example, an example might be OpenFOAM, which full installation of OpenFOAM is something like 10 gigabytes, I think. But to actually run OpenFOAM, you maybe only need 300 to 700 megabytes worth of actual software, actual files. So it means that we have a much smaller image to give you the same end result, right? You just have to pull in a lot less software, a lot less data. To access, so if you actually want to install, say, like on your own laptop or something like that, to access EC, you need to install CERN VMFS. We have some scripts to help you out here, but this is an example of what that looks like. So basically, you need to install an RPM, which allows you to dynamically update. It's our repository for our RPMs for CVMFS, or not ours actually, because they come from CERN themselves, and then that's automatically updated. After you've done that, you need a couple of key settings in your configuration file. One of them is just to say that you're talking directly to the mirror servers, that you don't have anything in between. But if you were doing a high performance environment, you probably would have something in between you and the mirror servers. And then you want to say, how much disk space am I going to give to the local cache? In this case, that's 10 gigabytes, so 10,000 megabytes. And then once you've done that, once you've configured things, then you just need to execute that setup, right? So you use a special command to do that. But rather than go through that, I think it's more interesting if we actually look at it in terms of a demo. Oops. So let me exit out. Exit out of this. Not to you. I need to. So to do that, I'm going to launch an instance, a cloud instance on AWS. To be a bit interesting, I'm going to choose Amazon Linux. To be a bit more interesting, I'm going to choose an ARM architecture. So hopefully, well, if you haven't seen an environment, an AWS environment before, this is typically how you launch a VM instance. I need a key pair to be able to log on to the instance. So I have one that I prepared earlier. I need to select the machine type that I want. So I want something with a little bit, a couple of CPUs. So let's say eight. Yeah. I can make this a little bit bigger. Different for me now. I might get one smaller, so it's the typical setup that I have, right? So that's all I need. So I just need to say what operating system I wanted, what size of an instance that I wanted. I needed to add a key pair, and then I should be good to go. I launched that instance. Okay, we can connect to it then. So it's up, because it's Amazon Linux, it comes up very, very quickly. So we can copy that connection. I have a little Jupyter Hub terminal here that we can use. So I just copy that connection information. It's a new machine, so it's not aware of it already. So now we're logged onto this system, and there's nothing available yet. So the first thing I want to do is install sudo yum install git, because there's no git on the system. All right, and then we have within EESSI we have this demo repository which contains some pretty useful scripts. So we're going to clone that demo repository over to our instance. So git clone, then the URL clone. The demo, and now we can go inside there, and we see inside there's a couple of different applications in here: Bioconductor, Espresso, GROMACS, OpenFOAM, TensorFlow, and so scripts directory as well. So we'll go into the scripts directory. One of the scripts, the first one here, hopefully that's big enough. Can you see okay? A little bit. So one of the scripts here is to install CVMFS and the EESSI configuration package as well. If you just run it, so if you just try and run that script, it'll say, oh, to actually do the installation, I need sudo, but here are the steps I would actually take, right? So this is what's actually going to run. So I won't go through those steps now, but they're essentially similar to what was on the slide for this particular environment, because Amazon Linux is a bit different. So we can use sudo on it now instead. And see, yeah. This takes not very long, about, I don't know, 20 seconds or so. This should be done. So it's just installing all the things that it needs to make CVMFS available. It's not doing anything else. Now we have a new location on the file system, and /CVMFS. Seems like it's empty, but it's actually not. Because if we know exactly where we're going, so software.easy.io with 2 E's, it auto-mounts that location, that repository, and we'll see that there's already things available inside. So as it was on the slides, we can source now files within that location. So we want to do our initialization. Right now there's only one version of EESSI available, but in the future there will be more added as we change over time. And then we have an initialization directory, and we want to initialize for bash. So here we see it's picked up the fact that we're using Architect, and it's picked up the fact that we have an Neoverse N1, right, as our thing. And as a result then, it's using all the software from within there. So now if we do module avail, we can see we have tons and tons and tons of software available to us. So let's just we'll look at maybe one of the demos that we have here. So we can pick, GROMACS is a good one perhaps. So in the demo for GROMACS, we can look at, there's a run script here called run.sh. We can just look at what's inside. Basically what it's doing is checking where it is and then loading the appropriate module. And then it wants to run a particular test case. If that's not available, it'll just download it. And then it will run a command with GROMACS. I'm not a GROMACS expert, but that's the command that it's running. So we can just run that script, and we'll see that it's downloading. Now it's downloading the data that it needs, and it's already running GROMACS, right? So GROMACS is now available on the system and running. This takes about this particular example takes about 20 seconds to run. I don't think I'll let it run through because we're short on time here. But it will run that example, and we can do the same thing for another thing. So for example, in bioinformatics, in bioinformatics, we could use Bioconductor. Same, we have a run script inside that loads the appropriate model. module and then runs a particular example. So we can run bioconductor as well. Again, it takes a little bit of time. That first run is going to take a little bit of time because it needs to talk to the mirror server to bring the files it needs to run local. But once that's been done, the second run will be a lot faster. So now you see we're running this bioinformatics application. And we can do that for lots of other applications that we have inside. The examples that we have are, the other ones are TensorFlow and OpenFOAM. TensorFlow is an interesting one because that first startup takes a bit of time because TensorFlow actually requires quite a lot of files and a reasonable size, right, about a gigabyte of data before it can actually start running. So that first run of TensorFlow would take a few seconds, but then the second iteration, because they'd be available in the local client cache, would run very, very quickly. Well, I'll leave that go because we can go back to the presentation now. So that's just an example of how quickly it is and easy it is to get this environment up and running in a cloud environment. And that's good, right? Because you've got all the software that you want to use or that maybe are useful to you in that environment. But what if there's something that you need that's not available in these environments? Can you get your own software inside? So we have a workflow for this. You, in this case, are a contributor. So you create a pull request to a certain repository, which is the EESSI, our software layer. Somebody will review that pull request, and that, as a result, then they can trigger a bot to try and deploy that. So we'll talk to all our build nodes for the various different CPU targets. It will build that information, and then it can also test it. So we have a testing infrastructure as well, which is based on reframe. When we build the software, this is one of the important differences, perhaps difference with EESSI, is we actually test the software that we're putting inside. So we run the test suites of the applications that we put inside. And on top of that, we also create reframe tests. So we typically expect that, good software practices typically have a test suite that they ship with their applications. So we run that test suite. But on top of that, we also want to run reframe tests. And we want to run tests that check not just does it run, but also how is it performing, how does it scale. We want to also keep track of that kind of information. So we run those as well. When both of these things pass, then we can create tarballs from these installations that are passed to an S3 bucket. A cron job then picks them up from the S3 bucket and schedules them for being merged into our Stratum 0, right? So this is our main copy of all our software. That scheduling opens a PR, so we don't automatically do that, but that opens a PR to a private staging repository, which is also reviewed then before it's actually deployed and made available through EESSI. So that's what adding software looks like. That's a very simplistic view because, of course, this part, creating the PR, it's only a one-line change typically in the software layer, but it relies on the fact that you have the recipe for that software already inside EasyBuild. So there is a little bit more involved there. So what's new? The software testing part is, or at least the reframe part of the software testing is relatively new. So we already run the test suites of the software that we build on the host when we build them. And we also have sanity check commands included in our recipes to ensure that the software that that's created is not horribly broken in some way. But then we have this portable test suite, which is based on reframe. It does the functional correctness part, but it also does, the idea is that it also checks performance, right? Single node, multi-node, that we keep track of this information. Not just at the time of the installation, but also over time, right? So we can run this reframe test periodically on different systems, which is what we're doing right now. We want to make sure that those software installations always work. And because things change. So things happen on systems, and then for some reason, software all of a sudden doesn't work. It sounds unusual, but it is the case that it does happen. Eventually, while we are already kind of gathering the information to help us do performance monitoring, but we want to make this much more accessible to people. So the idea would be that you have a website or a dashboard where you can go to see what's the development of the performance of a particular application over time. And to do that, then we would need periodic runs of this test suite to capture that information, but also to see when there are performance regressions in software as well. So in terms of the test suite, what's already there, we do releases of our test suite. So right now in the version 0.2.0, we have tests for GROMACS, TensorFlow, and the OSU micro benchmarks. We've integrated that into our CI pipeline when we build and deploy the software. What we haven't done yet is filter those tests because it's not a big test suite right now. It's only a few applications, so we haven't actually filtered based on the PR or anything yet. So each software contains multiple tests. The idea being that we want to test performance and also the scalability on different sizes, right? So different on a CPU, on a node, on multiple nodes. And the configuration of the nodes is, we want this test suite to also be portable. So the configuration of the nodes is abstracted away from each of the tests. So you configure for the site, and then the tests should just run, hopefully. And that's the idea, at least. So there's auto detection, there's configuration files in there as well. Our periodic tests right now are running in AWS using a Magic Castle cluster that we have. We actually have a few different Magic Castle clusters in that environment, also in Azure as well. And then on Euro HPC systems, so one example of that is Vega right now, which is in Slovenia. Only 5 minutes, right? So what else is new? We have GPU support. So NVIDIA GPU support. There's detailed documentation on this available. What were the problems when it came to NVIDIA GPU support? Well, one of them is that we have our compatibility layer, which isn't aware of the drivers that are available on the system, right? So we need to know where are those GPU drivers. And then the other thing is that we have the issue of licensed software, right? So CUDA. And we're not allowed to redistribute CUDA within the EESSI environment, but we are allowed to redistribute the runtime. So how do we deal with that situation? So we have 2 scripts that do that for us. So one of them is the one that finds the drivers on the whole system and puts them in the location. We have our own runtime linker. So we can put them in a location where our linker will find them. So we'll find those drivers and be able to run the GPU code that require the runtime. If you want to install additional software on top of the EESSI environment, then you're going to need that full, not just the CUDA runtime, but the entire CUDA package. And we have a different script then that puts that in a specific location. So there are some tricks that you can do with CVMFS that we leverage. One of them is something called a variant symlink. So basically you can have symlink within the CVMFS environment that you can configure in your configuration script. So right now the default location is in a location called /ops/EESSI, but the idea would be that, like for example, in an HPC system, you could point that to a location on your shared file system, right? So that you do the installation of the drivers once, and all of your CPUs will find them, right? So you don't need to do this multiple times. And so these are nice tricks that we can do because of the tools that we use. I was going to give a demo, but I don't have time. But basically, no, it's not enough. 2 minutes is not enough. It'll take me 2 minutes just to start up the machine. But basically, I was just going to show you that it really is that simple, right? If you have the CVMFS environment installed, if you have EESSI installed, if you try and load a GPU package, it will complain. It will say, oh, I can't see the drivers. Here's the web page that explains to you how to install those drivers. And then I would have run the script to show you that it will find those drivers. It will tell you what version of the drivers are, what version of CUDA is supported by those drivers. It will record that information, and that is leveraged then by the LMOD environment to figure out, can you run the software that we provide, right? So we have, say right now we're providing software that uses CUDA 11 point something, not sure. But basically we will check the CUDA version that's supported by your GPU and the CUDA version that we have, and make sure that you can actually run the code that we have. And if that's true, we will allow you to load the module, and I would have shown you then that a device query would have worked in that environment. What else is new? RISC-V support. So we're working on RISC-V support. We have a separate repository for that, where we're doing that right now. So we already have Gen 2 prefix support that was referred. We had done a project, a Google Summer of Code project already to work on RISC-V support for Gen 2 prefix. But that's been refreshed now by BSc, so here in Barcelona. And now we've made that available. We have a full toolchain available. So that means we have GCC 13.2, pretty recent OpenMPI. We have FlexiBAS. We have all those things we need to form an EasyBuild, what we call a toolchain within EasyBuild. And we've already started building software for that. So we were already up to building R and a large amount of packages for R. But we're working on that. It's very, very new for us. There's more details. For any of you who's at ISC next week, there's more details. We're participating in a workshop there on RISC-V, so you can see it there. CI environment. So you can leverage already EESSI in a CI environment. It's available as a GitHub action. Very easy to use. Basically, you just use the action that we have available, and you immediately have that environment, right? So just as you've seen, you could load a particular module and run whatever you have, right, in terms of your own code, right? So you can use it. So the idea here is to help people who are developing code to have an environment that they can reproduce themselves or in these kind of CI environments that's very, very easy and quick to set up. So this doesn't take any time, right? To get you something where you can actually load modules and run code, we're talking about 30 seconds or so, right? So you have all of our software stack available in a GitHub Actions environment within about 30 seconds. What's new is, so that was already available last year, but what's new is there are people who are leveraging this in the wild. So there are applications who are not directly connected with our project, but are users of codes that appear in our multi-scale project, and they are using this already. So in a nutshell, on-demand streaming of optimized software works on any Linux distribution, gets you a uniform software stack between all of the different CPUs and all of those different environments, and it's community oriented, right? So we hopefully engage the community, and we also accept pull requests and everything from the community. So the idea is this is not coming from one place, but it's a community effort. And then lots of other slides about acknowledgements and places to contact us. Thank you.
Thank you, Alan. We have time for one question.
Thanks for the talk, Alan. Two first small questions regarding compatibility. Are you supporting Zen 4 and AMD GPUs?
Zen 4, yeah, we're working on Zen 4 now. So we have a lot of stuff already for Zen 4, but we're not going to release it until we have everything the same as everywhere else. But we actually have built the entire stack that we have already. For Zen 4, we only had like one issue, I think. So it will be there. It's not there now. It will be there soon. AMD GPUs, that is the next step. It's a little bit, so we spent a good bit of time trying to figure out how we would integrate the NVIDIA GPUs. And now we have to do the same thing for the AMD GPUs. The nice thing is, because we didn't try to do this like a year or two ago, the environment is a bit more mature now. So this is becoming more and more possible for us, I'd say, than it was in the past. I think there's less obstacles.
And thank you. And the second question, how easy deals with the fact that if I want to have a modified version of a library because I want to change some compilation flags or some options when building software?
So, say this stuff is kind of work in progress, but we actually released something that would help you here. So obviously, we probably can't cover every possible use case. Like the idea, it would be nice if you could say, I can build, like for example, take the case of OpenMPI. I can build OpenMPI really fat, right? So I can support all of the different fabrics I can build an OpenMPI that supports all of these different fabrics. And then you, at the end user at runtime, can just set some flags that says, actually, this is the fabric that I actually have, right? So to improve startup time and everything. And it would be nice if every piece of software worked like that, but it doesn't, right? So we can't cover all the bases. We have to make some choices at some time. But the idea is that we want to be able to extend EESSI as well. So we have a module in there called EESSI Extend right now, as of like the last week, that allows you to load that module with the same settings that we use when we build software, which means that it will talk to the compat layer. It will make sure that it doesn't go outside that layer. And then you can rebuild a package, for example. So if you have the recipe, then you can rebuild a package or build a new package on top. We have to make it a bit more strict probably, because we probably need to enforce that you use the tool chains that we have, so that you don't try and build a new GCC or build a new OpenAPI, because it's likely that you will run into issues that we haven't run into yet, right? If you try and diverge greatly. But in terms of an application that's already there that you want to tweak, that would be the idea, right? That you would build your own version locally and that you could use that, or you could distribute that as well.
And if the application is not there, I have something and I don't want, because, for example, it's a code that is licensed, or I don't want to do this workflow of the PR, is EESSI able to do?
So this is the idea with EESSI Extend as well, is that so right now it supports 4 different modes. It supports building for EESSI itself, which you probably won't be doing, right? Building for in the host injection space. So that typically means a site installation, right? That you want to add something that's available on a site. It supports project-based, so that you can have within a certain group, that you want to share software with people within a particular group, and then user-based, right? So this is just for me, right? This is something that I just want. So that's what it supports right now. So it could build for all those different things.
So we are out of time, but let's thanks again Alan for his presentation.
you.